Hello everyone, my name is Arnel and I am a graduate student of Applied Economics and an electronics engineer working on a semiconductor company. And today I'm about to discuss about some brief overview about some emerging technology which is ReRam. It is actually one of the candidates to replace or somehow innovate the memory chip industry. And I will talk about some of the brief economics behind the industry, some technical overview about the materials and device operations, and some applications including the non-volatile logic and neuromorphic computing. So let's start first with some economics behind the ReRam chip industry. So we may want to first start with Moore's law, and Moore's law is not derived from the laws of physics, but rather an observation by Moore that the number of components, mostly transistors in an integrated circuit, doubles every 2 years. Unlike any other laws in economics or sociology, Moore's law did not use any empirical evidence on the continuation of the forecast of these historical trends. And it has been used in semiconductor industry to target their research and development plans. Example of this are advancement in shrinking of the size of sensors, increasing memory capacities of DRAM and flash, and digital electronics are linked to this law. So if you were born in the late 90s, and you'll actually notice how fast the transition from the old compact desktop computer, which is nice to have during that time. You could do office works like creating work documents, even playing music. But with our computers right now, we can play very high definition computer games and stuffs. So in the following slides, we're about to know some ways on how the manufacturers increases their profits by reducing their cost. One prediction in the 1974, Robert Denard described the physics of MOS, or metal oxide semiconductor transistors, have some scaling factors. He said that if you scale its dimension by a factor of lambda, as well as the doping concentration, voltage, or current, then we can get a transistor that is not just smaller but also faster and also uses lower power consumption. The transistor gets better as you shrink until it's not. There's some endpoint to this because we can no longer bring the voltage down, and the voltage of these devices are actually less than a volt, and it is very hard to make it any lower because of the presence of thermal noise, which is around 25 millivolts. Now when the transistor gets smaller, it uses more power, it gets noisier and be slower. So to keep it working correctly based on what we want, even though we have constraint in manufacturing cost, we have to do some sophisticated engineering works to modify the transistor. Say for example, if you were the owner of the company, you want your business to scale and you want to supply the demand. And if we come to the point that we cannot make the transistor any better, we have to make our chip smaller so we could produce higher density or higher gigabyte per area at minimum cost. Engineers do this to lower the cost per function. Lowering the cost per function means in a memory chip is increasing the memory capacity of the same wafer area. So we can say that Moore's law is about cost. The economics is when manufacturers keep the cost per unit area constant. So as they squeeze down more and more transistor into a given area, the cost of making that area stays the same. Therefore, the price of each function per transistor goes down. Manufacturing yields were relatively low in the 70s. It's just around 20%, and engineers thought that they were doing pretty good but with their low yield, but they figured out how to raise their output over time through some sophisticated manufacturing techniques, and they noticed that the primary thing that causes the failures were manufacturing rejects. So just to clarify these terms, we have a term like defected unit from electrical rejects, which means that the quality of the unit below the set standard is not accepted and should not be shipped to the customer. And manufacturing rejects that can be avoided, like setup-related failure, test program-related issues, and electrostatic discharge from operators. If the overall rejects are significant enough, reducing these rejects due to some manufacturing errors has been critical part of yield improvement. And by the 80s, yields were around 40% and went up again to 70 to 90%. But the problem is once you hit 90 to 95% yield, there's no room for improvement So if you have that kind of yield, so it's only a small improvement in cost. So today it is somehow standardized to keep manufacturing yields high enough, above 95%, which is hard thing to do. And there's no more room for improvement in lowering the cost by increasing the output. So again, manufacturers wants to lower down the cost so that they will have more profit. And the other way that they've been able to lower the cost as complexity increases is by increasing the productivity of their manufacturing tools. One of the cutting edge tools in the semiconductor industry is lithography tools. Lithography is just a printing technology that prints the design patterns of our transistors on each wafer. And these tools, like the cameras, are very expensive. In 1979, these cameras or steppers was about $500,000. By 2012, just around $50 million. And of course, we're not accounting yet for inflation, but still an expensive technology. And by this year, 2022, the company ASML launched EUV, or extra ultraviolet lithography, which is a new cutting edge technology. One machine just cost around $200 million to sell. So they create a short-term monopoly in that lithography business because they're the only one who can sell. Their product mainly targets the 5 nanometer range transistors and somehow reduce the cost per function, or could increase the memory density of a particular transistor device. Now, seems like it will be hard to keep the cost low when the capital you need for that equipment goes up. But we may not notice is that the productivity of these tools also increased. And also, probably there will be a short-run monopoly. They can actually dictate the price of their product and somehow pass the cost to their customer. So the other way in which manufacturers been able to lower the cost of making a chip is with wafer size. Whenever a new wafer size were introduced, the cost per area of silicon is at maximum. But as technology progresses, this cost per area drops with time. A concept in macroeconomics might help us understand the effect of ReRam entering the chip industry. So as shown in the graph, we have a production function where the inputs are capital, labor, and the multiplier is technology, which denotes for variable A. And as you can see, there's a diminishing marginal return, which as we increase inputs such as capital and labor, the rate of output decreases. But as we approach the limits in physics, the cost goes up, probably because there are instances that we may need more capital expenditures for some cutting-edge technological tools, and we may also find that there is a low supply of expertise in the labor market, which could also drive the cost, which is not worthwhile doing anymore. And as a result, the observation is that the budget runs out before you hit the limits in physics. Well, if you're going to hit an economic limit, there should be an innovation in which ReRam could be a thing. We could come up with some new way of doing things, probably new circuit designs, new hardware techniques, and new manufacturing techniques. There's a lot of possibilities for this technology, and if we push closer and closer to the new physical limit, the cost could go down because there could be more competition as we approach the long run. The new economic limit has now much greater capability compared before. So we need more innovations in order to have more economic growth. So now we're about to know some overview of what is ReRam, or sometimes called RRAM, the technical overview about the device operation and some material used and some applications. So first, I'm going to further have a brief introduction on what's already been there for the random access memory, which can also be referred to as RAM, and it can be volatile or non-volatile. RAM, of course, we already familiar with this. We have this in our computers, smartphone, and smartwatch. So a volatile memory loses its previous stored data by removing the power supply, as in the case for dynamic random access memory, or DRAM, and static random access memory, SRAM. DRAMs employed in a computer system has high capacity and density, but they are volatile, meaning there is need to refresh every few milliseconds. Due to this refreshing, the energy consumption of the device increases, which we don't like. So just some basic principle of storing the binary memory is when you force a voltage into the gate of the transistor so that the current will flow into the capacitor coming from the bit line, so that charge in that capacitor is now the stored stored memory. SRAM, on the other hand, is much faster. It is also volatile, just like DRAM. SRAM cells are larger in size, which somehow hinders its implementation on a large scale. So it is a 6 transistor memory cell, because an inverter can be a 1N type and 1P type MOSFET transistor, which the overall count is 6 transistors. So for non-volatile memory, the data stored previously will continue to be retained even after the removal of the supply. An example of this is flash memories. Flash memories, which is essentially consist of floating gate MOSFET, is currently being used extensively, particularly for embedded applications due to its low cost and high density. And just the basic principle of it is that there is a specific threshold voltage applied in the word line for each control gate of floating gate MOSFET, so that you can do parallel or series of these transistors and control their logic states. Depending upon how memory cells are organized, flash memories are classified as NOR flash and NAND flash. In NOR flash, cells are read and programmed individually as they are connected in parallel to bit lines. This looks like a parallel connection of transistor in CMOS NOR gate architecture. For the case of NAND flash, the architecture looks like a CMOS NAND gate, as the cells are connected in series to the bit lines. It consumes much lesser space by the series connection as compared to the parallel one, which result in reduced cost of NAND flash. So these memory technologies are charge stored base memories. DRAM stores the information in the form of the charge in the capacitor. SRAM is based on the storage of the charge at the nodes of the cross-coupled inverters, and flash memories use floating gate transistor to store the charge. All these existing charge store based memory technologies are currently facing a challenge down to 10 nanometers beyond. This is due to the loss of stored charge at the nanoscale, which results in the degradation of the performance, reliability, and noise margin. So a new class of memories are currently undergoing development and is being actively researched primarily in the semiconductor industry, with the aim to revolutionize the existing memory technology. These emerging memory technologies aim to integrate the switching speed of SRAM, storage density of DRAM, and non-volatility of flash memory. Thus, it became very attractive alternative for future digital memory. So resistive memory technology is actually a memory store. The original concept of it was first conceived by Professor Chua in 1971, and he said that in the IV curve, if it's pinched, it's a memory store. And in his works, he said that there is a missing electronic component that links electric charge and magnetic flux, and that could be memory store. A lot of current research in resistance-based memory technology are actually significant to what Leon Chua had predicted. Say the capacitor first discovered around 1745, resistor is 1827, and inductor was around 1831. And they have been only the fundamental passive devices ever known. Each of these passive devices performs at its own characteristic that is unique among others. Like for example, capacitors stores energy in an electric field, inductors store energy in magnetic field, resistors dissipate electrical energy. And Leon Chua proved theoretically that the behavior of the memory store could not be substituted by a combination of the other three circuit elements. Hence, he says that memory store is a fundamental device. Like in an example of HP's memory store, they've started with a layer of platinum, which is their electrode, and then deposit some titanium dioxide on its top. So by applying a positive step voltage, it pushes oxygen atoms, making oxygen vacancies. So if you remove oxygen atoms from titanium dioxide, it becomes metallic, and therefore the resistance is low. Then vice versa, by applying a negative step voltage, it brings back those oxygen atoms to the titanium dioxide, creating a high resistance state. So that is a short introduction to memory store currently currently we have various emerging memory technologies that are actively being investigated to meet these ideal memory characteristics. And these technologies depend upon the change in resistance. So we have something like phase change memory or PCM, spin transfer torque magnetoresistive random access memory or STT MRAM, and resistive random access memory or RRAM. So in phase change memory, the switching medium consists of chalcogenide material from an alloy of germanium, antimony, and tellurium with a stoichiometric ratio of 2:5 as shared in public. PCM relies on the difference between the resistance of crystalline phase and amorphous phase for data storage capability. The crystalline phase denotes the low resistance state or the on state of the device, whereas the amorphous phase denotes the high resistance states or the off state. In PCM, the heat is produced by the passage of an electric current through the phase change material through what is called the Joule heating effect. And when heating the amorphous material to a high enough temperature but below the melting temperature, it will rapidly crystallize. Now, to transform the material back to amorphous phase, it needs to be heated above the melting point, the melting temperature, and then rapidly cool down. This rapid cool down will freeze the atomic structure and in a disordered state. So notice that the more disordered the molecules in the material, the higher its resistance. And that is the case for amorphous phase. And vice versa, less resistance means approaching crystalline phase. For STT MRAM or spin transfer torque magnetoresistive RAM, the storage capability is due to the magnetic tunneling junction or MJT, which consists of two ferromagnetic layers and a tunneling dielectric sandwich between them. So the magnetic direction of the reference layer is fixed, or sometimes called the pin layer, as shown in the graph. The application of current can change the magnetic direction of the free layer if the pin layer and the free layer have the same direction of magnetization, or the layers are in parallel. The MTJ is referred to be LRS or in low resistance state. For MTJ to be in high resistance state or HRS, the direction should be in anti-parallel. So the two ferromagnetic layers direction is anti-parallel. So for the RRAM, it consists of an insulating layer that's sandwiched between the two metal electrodes. So RRAM relies on the formation of conductive filaments corresponding to LRS and HRS. And it has been observed that in some insulators, the change in resistance occurs under the application of applied electric field. This change in resistance has recently been investigated for non-volatile memories, and we will talk about that later on for the application. So the resistance switching phenomena has been observed for various variety of oxide like hafnium oxide, titanium oxide, tantalum oxide, nickel oxide, zinc titanate, manganese oxide, magnesium oxide, aluminum oxide, zirconium dioxide. So these materials have drawn the most attention and have been studied extensively during the past several years. So the switching mechanism of RRAM cell is based on the growth of conductive filament inside the dielectric. This dielectric is very small, just around nanometers in scale, that connects the top electrode and bottom electrode. So the composition of the conductive filament are classified into two. One which is the metal ion based RRAM and can also be called or referred to as CB-RAM or conductive bridge random access memory. And the other one is ReRam or oxygen vacancies filament based resistive random access memory. So ReRam switching results to redox reaction or reduction oxidation reaction. The mechanism of CB-RAM and ReRam is a little bit complicated because it depends on the material, but in simple terms, for CB-RAM, when applying enough positive voltage, it oxidizes the metal atoms into ions because of the applied electric field, the metallic filament grows until the top electrode and bottom electrode are are connected, which indicates it is a low resistance state, and it can be reversed by applying a negative voltage, which is the case for high resistance state. A simple explanation of ReRam is when an electric field is applied, it removes the atoms from the oxide material and becomes metallic, which creates a low resistance state. And by applying a negative step voltage, it brings back those atoms, creating a high resistance state. These memory stores are ideally can have more than 2 bits of data. So right now, our semiconductor devices like MOSFETs can only function as ones and zeros, which is just turn on and turn off. But for memory store, it could have beyond that. Could be that one memory store cell could have 3 to 4 bits of data. It can happen because resistance is analogous in nature. It is not discrete. In actuality, some research found that it can happen by increasing the compliance current, or compliance current is some sort of current threshold, or increasing the reset voltage of the device. This actually depends on the material and the corresponding IV response. So in the figure, we notice that by increasing the compliance current, we only have one high resistance state and 3 low resistance state, which is equivalent to 4 bits of data. Can also be by increasing the reset voltage, which we have 1 low resistance state and 3 high resistance state. So researchers also finding some way to increase the density per area of the device. ReRam or ReRam is one of the candidates among the emerging memory technologies that have the potential for reforming our current memory technology due to its high speed. It is high capability of non-volatile data storage and enhanced storage density and logic computing function. So one application of ReRam is non-volatile logic. So we have, say for example, we have an instruction codes and data that are being moved between computing memory and memory unit in a computer system in which it is a von Neumann architecture. This data transferring process results to an increased energy consumption and time delay, which is commonly referred to as von Neumann bottleneck. So to reduce the impact of von Neumann bottleneck, the computing process is suggested to utilize ReRam crossbar array, because this will change the memory and computing operation in the same core. Say for example, to have a simple Boolean function such as logic AND, logic OR, and logic NAT, we should have multiple transistors to do that operation, where each transistor takes 8 units of 10F squared area, whereas the same logic function could just use 2 or 3 ReRam memory cells, which is just around 1 unit of 10F squared area only. And we know that Boolean computation is significantly more established compared to neuromorphic computing and quantum computing. Therefore, the energy and cost efficiency of CPU or MCU can be enhanced without the need to develop new algorithms or software. Most of research focus only on the basic logic level, because it becomes complex to implement a whole computing unit using ReRam array. To overcome von Neumann bottleneck, one solution is to have a brain-inspired neuromorphic computing. The potential of this is seen in a wide range of complex and cognitive tasks like audio or visual recognition, self-driving cars, and real-time big data analytics. Neuromorphic computing actually mimics how our brain works, and it is much faster and consume lesser energy. Fortunately, our brain doesn't actually function like a von Neumann architecture, because we don't have CPUs in our brain. So we don't suffer from von Neumann bottleneck. So when we see a cat, we know that it's a cat because, we have seen a lot of cat in our lives. But assuming we don't know it yet, we don't know that kind of living thing is a cat, and we will just know that it's a cat through feedback and repetition. It is when our kindergarten teacher will teach us that it's a cat, then we will know and somehow verify that it's a cat. And through years of seeing this cat over and over again, we are now convinced that it is a cat. And it's now a no-brainer to you that you cannot doubt yourself that it's a dog, right? And yeah, we know that artificial intelligence nowadays is now a thing. And AI can be implemented in 2 ways. It can be on a neuromorphic computing or an artificial neural network. Artificial neural network is inspired by biological neural networks. just like a human brain, an artificial neural network is constantly learning and updating its model based on its input data. Neural network is really a big word in neuroscience and data science, and will really take a lot of time and effort in order to understand those big concepts right now. But right now, what we want to know is why use memory store? Well, compared to CMOS-based neuromorphic computing or CMOS-based neuromorphic network, neuromorphic computing based on ReRam array have the advantage in terms of on-chip weight storage and scaling up to a much larger size of array. It was then realized that the hardware implemented neuromorphic computing archetypes have two methods, including strategy of mimicking the structure and working mechanism of biological neural networks, while the other method works on accelerating the existing artificial neural networks, or ANN algorithms. In a biological network, there's a thing called synapse. In simple terms, a synapse is just a small gap between two neurons where nerve impulses are relayed by neurotransmitters from the presynaptic axon or the sending neuron to the dendrite or postsynaptic receiving neuron. While in artificial neural network, a synapse is used to transfer spikes between different neurons in addition to storing information regarding about the information about transferring weights. The information regarding weights can be acquired through certain learning rules such as spike time dependent plasticity. So the figure on the upper right shows an example of a single memory store device acting as a synapse and reproducing STDP behavior or of biological synapse. So like in a biological synapse, a memory store can store at the same physical location. Remember in the titanium dioxide example, when we force a positive step voltage, the oxygen atoms are ionized, and when the slope of the voltage is now negative, it produces some oxygen vacancies and turns out to have some resistance which can be used as a memory. So thank you very much for listening.